Okay, hello and good evening to all of you. I think it's being globally attended. So, this is a great pleasure to host or co host today's session, which is an institute series of lectures on Saturday manufacturing talks being organized by the Center of Excellence on Advanced Manufacturing Technology. And today we have with us Professor Debdoot, who is with IIT Kharagpur to throw lights on the topic of vision for anomaly detection in steel manufacturing. Before we start and I pass it to Professor Debdoot, let me just briefly introduce Professor Debdoot. So Dr. Debdoot is an assistant professor of electrical engineering with a joint appointment at the Center of Excellence in Artificial Intelligence at the Indian Institute of Technology, Kharagpur, and founder of Skincare Research. He also serves as Joint Project Director of the IIT Kharagpur AI for ICPS 1 Hub Foundation. He received the BTech degree in Electronics and Communication Engineering in 2008 from the West Bengal University of Technology, Kolkata, MS and PhD degrees from the Indian Institute of Technology, Kharagpur in 2010 and 2014, respectively. His current research interests include deep learning, high-density multilinear algebra, computational medical imaging, image and multidimensional signal processing. He is a chartered engineer since 2021. He is a DAAD alumni and was a visiting scholar to the Technical University of Munich during 2011-12, recipient of IEEE Computer Society Richard E. Merwin Student Scholarship in 2021, the Fraunhofer Applications Award at Indo-German Grand Science Slam 2012, winner of GE Edition Challenge 2013, distinguished alumni of IEM Kolkata 2016, senior member of IEEE class of 2019, member of MICCAI, life member of IE India, BMESI, IUPRAI, and serves as regional editor of IEEE Pulse. He is the local organizing chair of IEEE International Symposium on Biomedical Imaging, ISBI 2022, Kolkata, India. So, I welcome Dr. Debdoot for today's presentation. And as we know, the advanced manufacturing is the key for next couple of years, and it will be one of the things which all the manufacturing units should reorient themselves to tune to the recent available technologies and adhere to different production targets while maintaining the safety and quality and environmental aspects. So to give a brief of the abstract for today's topic on vision for anomaly detection in steel manufacturing, is being manufactured through a continuous process that has a requirement for persistent monitoring across its various stages. One of the challenging ones being the quality monitoring of the finished product of the rolled steel plates. Since the hot rolled steel plates are exposed to several roller mills which operate via electric motor drives, and several of the faults which may occur in the electric machinery causes a spectrum of physical rolling damages, physical rolling which damages and it causes on the surface of the steel plate finishing some anomalies. So it's important to continuously monitor them. However, this is easy to discuss and it's easy to think, but getting it operationally implemented is really a challenge. So it's challenging, and since the nature of the faults are quite varied, as well as the general alloy compaction stages of the steel, which makes this problem of finding anomaly is in dynamic background becomes very, very difficult. So we address this challenge using vision-based anomaly detection and interesting interventions of deep neural network-based learning rules to achieve the anomaly detection on a dynamic background. So that's very, very challenging, and that poses a lot of research avenues to this topic. So with this, I welcome Dr. Debdoot to present, and let us get enlightened with his vast experience and exposure. Dr. Sheet, please. Yeah.
Thank you, Professor Chakravarty. It's an honor to actually be invited over here for this particular talk. Now, manufacturing is an area where per se I don't work. Most of my work is actually on healthcare. And this somehow happened to be that I got approached by folks at Tata Steel who were quite persistently pursuing me for almost a couple of years that we take a look into the problem which they were facing, and they already had a solution. So first and foremost, I hope my slides are visible. Okay, great.
Yeah.
So in fact, the bigger problem is that since I don't come from a background in manufacturing or anything to do with process industry or anything to do actually with industry, most of my life in research as such, I've been spending more time in hospitals trying to understand what happens in disease processes than ever try to dribble into what happens within a actual manufacturing plant. And plant to me is generally all the green plants which do photosynthesis. Nonetheless, so when I started, this was a huge learning experience for me because it took me a series of trips to Jamshedpur whenever I could get time in order to understand where the whole problem is. So today I did make an attempt at the best to convey it. However, I have a disclaimer just at the bottom of my slide. So this is a highly protected IP, and this was jointly done with Tata Steel. It's still a work in progress actually. And what I am presenting today is actually a surrogate of the actual model which is deployed, in a sense that this was put into production, this was tested out, and then it was pulled out of production because we have a better model currently running over there. So this is something which is currently not on the actual tests, on the actual production monitoring server over there, but has been pulled out after a series of tests. And so this is something like which is okay for me to discuss amongst people because nobody is going to use it anymore. But and also it was bigger challenge to prepare these slides because I cannot show a lot of those images itself. They are all images from within the Tata Steel plant in Jamshedpur, and it's totally restricted. So I tried to pull out as much as images possible from steel.org and all the other websites where they explain about steel technology and open source images which can do the best of it. There are still challenges where I would be doing more of speaking, and you will have to still imagine what it might look like because I cannot give you images of the camera. The whole imaging setup itself is quite unique, which we built up over there. And it was so unique and so protected that they did not even let a vendor go out of the plant to do it. So there was a camera manufacturing vendor who was brought inside the plant and given down a place, and they said like you will assemble the whole camera, you will assemble the illumination, the whole light box. They fabricated a complete box over there and fit it over there, and then they were let to go out. This was the level of private. I mean, I do work with defense establishment, but this was some other level of discreteness which was being faced out. Anyways, let's go through it. So first and foremost is a standard disclosure which I give out. So all the people over here, they had sponsored our research group at some point of time, and whatever you are seeing over here is a cumulative effort of over the years of these things coming out from here. Now, first and foremost, I believe most people on this forum are much more well versed about this whole process of steel manufacturing than I am. I'm a novice to this one, and all of this is more of a cartoonish picture which you can ask a kid to understand in order to understand what would happen in a steel plant. But for my purpose, this is something which is really interesting because this summarizes exactly where we are looking at. Now, this particular block, which comes up in red, consists of these slabs and thin slabs. This is the point of intervention where we look into with the camera and try to understand what are the defects. Now, if you look through this whole plant, there are actually vision interventions which we are doing at the level of the coke oven itself. We are doing vision interventions at the level of this iron ore injection into the actual plant, into the redox plant. We are also doing certain vision interventions in the level of recycled steel as well. So these are different projects which we are currently carrying on with Tata Steel. But what I am speaking today is one of those which has actually gone into a test server, been over there for a year, then has been pulled out for a new model to go in. So which is a actual thing which is a software which has gone through the whole research phase and is now actually in deployment. So now what we do over here is that typically, if you look at the almost the end part of the continuous manufacturing process. So after this, whatever comes down is the discrete steel manufacturing. So you would have you would have rolled pipes, you will have thin sheets, you will have rods, all of these things being created out over there. But the end phase of this continuous manufacturing is when you are going to get down slabs or thin slabs, and or you get down these kind of blooms and billets coming out of it. So blooms and billets are not much worrisome as such, though there are some defects in terms of in blooms. We did identify one of the defects, which was the thickness inhomogeneity over there, as well as some sort of molten defect cracks which come down over there. But in case of slabs and thin slabs, these are much more critical because they impact the quality of the outgoing product, and as such, it can actually lead to a lot of commercial losses. So to give you a very simple example, what happens out with the slab is this slab is sort of about 5 to 6 inches thick when it comes out over there. And by the time it comes out of that roller mill, the slab is actually not completely cast. So it's still in pretty much a molten condition in the central part. The periphery is what is completely casted. And so even if you find out a defect, it's really hard to rectify at that particular point of time, except for like you need to again push it back into the rolling mill after a reheating furnace part of it. Now, as of today, because that steel comes out still in a process stage, so there is no way that you can inspect it. So you can have a human being stand in front of it, but you can imagine how hot it is. And it's not at all possible. Next, on top of it, because it's so hot, so it's emitting a lot of infrared radiation, which is again harmful as a workspace problem over there. So we cannot have human inspectors. So the earlier challenge was like earlier solution was you deploy a ton of human inspectors, but with current factory regulation laws and all workspace hazard associated laws, we cannot have human inspectors over there who can visually inspect it. Now, what comes out as a problem is that if there is a defect, you cannot sell it out into the market. You will have to actually send that iron back into a reheating furnace and then again through the mill in order to correct for the defect. Now, the issue is that the steel slab, which is 6 inches, it takes about 3 days in order to cool down when a human can go in front of it and investigate. So technically, if there is a fault, so the earliest you can identify is after 3 days. So if today there is a fault in the whole roller mill, then after 3 days, I will be able to find it out. Now, and in this 3 days, whatever production has come out of this rolling mill, everything is indifferent. So that's where it creates a huge loss. Now, on top of it, what happens is because this slab has cooled out, so if you have to send it to the reheating furnace, it consumes a lot of energy over there, and that actually escalates this total expenses in order to create this material. Now, instead of that, if we are able to really identify it right at the spot before it starts cooling, so while it's still in the alloy stage, it has not yet cooled out completely. If we can identify these defects, then the energy consumed in order to reheat is much lesser. Plus, the intervention which can be provided is pretty much in real time. So as of today, we have this 30-second intervention pipeline over here, which is pretty much within the length of one single slab, you can stop the rolling mill, or you can redirect the flow to another rolling mill, or maybe slow down in order to look into a intervention over there. So this is what we are looking as of today. Now let's look into what comes out from there. Now, generally what happens is you would have this continuous cast which is coming down. Now this continuous cast needs to be pressed into a uniform thickness. That continuous cast is generally a bit wavy and non-uniform in nature. So now that it has to be cast to a certain fixed thickness, so it passes down through these unidirectional rolling mills. Now when we look into thin slabs, then what happens is that after this unidirectional rolling mill, that it comes down with the standard thickness, generally about 6 inches or so, then it passes through a slab cutting machine over here. And after this slab cutting machine, you typically get down standard slabs over there. So about 3 meters in length or something is what a standard slab is. And then this slab goes through another set of rolling mills, which are bidirectional in nature. So they rotate in both the directions. Now, these are again DC motor operated. What they do is something like what you would do in order to roll a roti. So basically you take a rolling pin and then you are rolling it back, and so forward and backward, forward and backward. So a bidirectional rolling mill does the same thing, and that essentially squeezes this in order to turn it into a very thin slab over there. And these can be really made as thin as 2 millimeters itself, which are basically tin sheets as we know them today. Now, I'm not looking into the other side of the bidirectional rolling mill, but I'm essentially looking at all the defects which happen in this unidirectional rolling mill, as well as the defects which happen in this torch cutting stage. Now, let's look into the first one. So in this unidirectional rolling mill, there can be certain defects which happen because of the mill. So these motors in the mill are generally AC induction motors. So these are all three-phase AC induction motors, which are about 10 kilowatts or so nominally. Some of them like really are in the order of about hundreds of kilowatts over there. Now, these rolling mills can have a couple of these kind of defects. One of them can be that the roller jams in some way, and then it's not so hard for it to get jammed because there may be some molten steel. It was not yet completely cooled down, so it just got deposited over there, and that went on jamming something. Or you basically have a lot of these rotatory parts. You have gears, you have shafts, and one of them had some sort of a defect, and then it jammed out. There are also motor defects related things. So you have an AC motor which is rotating at a constant speed, but then here the issue is that because it keeps on coming over here, so there is a thick plate which comes, and then you need to press it down in order to make it thin, and it's not continuous. You're also cutting down over here on one side, so the load profile actually keeps on going up and down. So that in typical AC induction machines, you have this torque speed characteristics. So essentially the torque keeps on changing, so the speed also keeps on changing for this motor, which leads to a back EMF change over there on my AC power line. And that can lead to a lot of challenges within the complete drive circuit over there. So that can induce problems in the motor itself. And if there is a defect in the motor, suddenly like one of the motors will not be functional. Now, in this roller plate, what they have is on both the sides, they have two motors which are synchronously rotating over there. Now, if one of the motors stops, then you would not have a uniform rotation over there. So one of the sides will rotate faster, another will rotate slower. So you can imagine this to be something like you are trying to roll a roti with only one side, and then you get a wrinkled out appearance of the rolled out product over there. Then on top of it, there are these issues with debris which stick onto rollers. In fact, this is the most common of the defects which happens. So the roller itself is also a stainless steel thing, and then some molten steel actually gets stuck on that. So this is something like it will keep on rolling back and forth on top of it. And then every time this debris actually comes in contact with the surface, it's going to create a small groove or a depression over there. And that impacts the total surface quality. So I have some pictures I will be showing about what they look like. They look pretty interesting in its nature. Now, this is one of those kind of images which shows a pertinent defect, which is called as a groove mark. Now, the most common is actually a groove mark. Now, groove marks can happen because of any of these three regions. If you look very closely into a groove mark, now there are specialists over there who can actually look into a groove mark and say what is the reason for that groove mark, whether it was a jammed roller or whether there was a debris on the roller or whether there was a motor which was jammed or there was a motor defect over there. So this is also pretty much possible. There is no issues with that. But we are looking at a general scenario of looking into a groove mark over here. Now, there are defects which are induced with the next stage, which is with this cutting over here. Now, what can happen is that when you are cutting it down, now there is a flame torch which is essentially cutting this steel. So there is a flame torch which moves synchronously with the speed of the steel, so that you have a very straight line cut over that, which is orthogonal to the direction in which the steel slab is. However, because there is a gas torch which is cutting it down, sometimes there can be these molten deposits of steel which stay at some places. Or what can happen is that while it is cutting, the cutting might not have gotten over completely, and the downstream roller, which actually rolls it faster because it has to pull out the slab from that continuous block which is coming, continuous slab which is coming out. So now if that one starts rolling faster before the cutting has gone over, then you will have a wear and tear at one of these edges over there. So there can be these kind of dragged edges, or it might so happen that when you are cutting across the length, it did not cut it uniformly. So you had a dragging of that edge. So it will look like a torn up paper. However, it looks like this will be a torn up steel at the edge. Then there are these unsmooth cuts over there. So essentially there is some sort of a jaggering of the cut, or it may so happen that there are double torches which are used in order to make it a smooth cut. One of the torch does not blow out properly, so the cut is not actually done properly. So these are these different set of defects which I would be showing out over there. Now, one of these is, this is an example of what an abnormal cut looks like, and this is another example of what a burr looks like. Burr is because of this drag cut edge. So over here, it looks like as if somebody has torn out a part of that steel and kept it over here. Now, something which is very interesting to look into, and that's what I was mentioning in the abstract, is the steel is actually at different level of alloy compaction process. And as a result of which, when you look into the image, the appearance of the image largely varies. So actually the steel slab over here on the abnormal cut is completely stretching from the top to the bottom. But at the periphery, you won't get to see it. The reason for that is that in the center, it's still in molten alloy phase. That's why it's emitting a lot of infrared radiation, and it's pretty much visible. On the periphery, it's completely cooled out, so it's darkened. On the other side, where you see a burr, it's actually cooled out uniformly. So the ambient illumination which is on it, the reflected light is pretty much uniform. It's not getting guided only by the IR. The illumination compensation is working on a uniform way, and that's why you are able to see the complete slab. Now, this is another level of a problem which we face, that the background is never static. The background keeps on changing, and you just have to live with it. There is no other way of getting to solve it out. Now, if you look into this whole solution as such, and how it works out is something like this. Our intervention consisted of putting down a camera on the complete roller on this like slab rollers over here. So there are these cylinders over which the slabs are rolling out and they are coming out. And then you basically have a bifurcated pathway. So you, based on whether you have a normal one, you channelize it out through one of these pathways. So this goes out into the exit route. It does not re-enter the production route. If you have a problem, then channelize it into the other side of it. And that goes into a manual inspection routine. And then based on the manual inspection, it will be assigned into one of these re-entry stages. So either it goes lower down to the scrap iron re-entry stage, or it can just go into a reheating oven. And from a reheating oven, it again comes into this same route over here. So this whole part is what consists of the total production assembly pipeline. We did not really touch anything on that. Where we needed to have our efficiency done was whatever feed comes from the camera in terms of these images. Now they need to be processed out so fast that the rate at which these steel slabs are rolling out, you can make a decision by the time this steel slab comes into this junction. You already have a decision whether to move it to the orange line or to move it to the green line. So if it goes into the green line, then it enters into manual inspection. If it goes to the orange line, then it basically goes out into the exit line over there. Now, this is what is a real challenging job to do. So if you look over here, this is an example of how the images were coming to us. And honestly, I cannot show you real images from where this whole assembly was created. The reason is that it is completely locked out. But I'm trying to make as much as illustrative visualizations of what happens over here. So typically you have a roller plate on which the slab is rolling and coming out, and you have a camera over there which is static. Now this camera is acquiring multiple images, and we are looking at typically 4 snapshot images per length of a slab. So this is the slab which comes after the cutting has been over. It's a fixed length slab. Now for the length of this, for the fixed length slab over here, I'm going to get down 4 images. Now the first image is called as the head image, which is the one which is marked in red. So this is at the start of the slab. Next, I get down 2 images, which are full body images. Then I get down the tail image, which is at the end of the slab. Now defects are, so whatever defects are corresponding to these cutting edges, they can be in the head image or the tail image. And wherever we are encountering these defects due to roller problems, they are something we encounter predominantly in the full image, full body image over here. But there are traces which we see in head and tail. However, in order to keep it simpler, what we do is we have a pipeline created such that we divide this problem into 2. So we have one routine which just looks into the defects of head and tail, which are essentially cut related defects. We have another pipeline which looks into surface defects, which looks into full bodied images in order to ascertain what are the surface defects which come over there. Now, in these kind of full bodied images, what we look into is essentially groove image, whether there are groove defects. So all images which were there in our training data set, as well as our validation and everything for the machine learning perspective, they consisted of images which were either categorized as groove mark images or images which do not have any groove mark over there. So they are the N groove or the not a groove class of images. And we did not make use of head images as per our protocol. We were all discarding head images. We were just using the protocol of using only these tail images. Now, you can use either head or tail. For us, using a tail image was what is more important than using the head image. So we just went around with using the tail image. Now, on a tail image, you can have these different kind of defects over there. One is there can be an abnormal cut. There can be a D-cut or a double cut. Essentially, as I said, so there are 2 torches which are basically blowing flame in order to cut it down. And say for some reason, one of the torch did not have enough of gas being pumped into it. So the total flame power was low. And as a result of which, the cut was not proper over there. So that can lead to a D-cut problem. And N-cut is a normal cut. There is no defect over there. Or there can be these burr marks. And these 4 categories of images are what are present over there. Now, interestingly, there is something more I would like to indicate. So if you have defect of any one of these categories, you need to call that slab as defective. Next is you can have multiple of these defects occurring together. So there can be a burr mark along with an abnormal cut. There can be a D-cut along with a burr. Generally, abnormal cut and a D-cut don't come together. So that's an interesting part at least. So if there is an abnormal, if there is a D-cut, it will just be a D-cut. You will never get an abnormal cut. So a double cut will never leads to that. But double cut and burr together are very common, and abnormal cut and burr together are also very common. And separately, a lot of these problems are burr defects which you see over here. So if you look into these images, now certain interesting points. So when you are looking at the head image or the tail image, you would see a part of this roller. So you see these steel rings on the right hand most side of these images. Now, these are those rollers on which it's rolling and coming out over there. Now, when I'm looking at the tail image or the head image, I would always be getting these rollers. Whereas if I'm looking at a full bodied image, I will never be getting to see those rollers. So that's another issue with the background. So the background itself keeps on changing. Now, what we did is we also had an additional category of background. So in case sometimes you accidentally get some images from the synchronization pipeline, because from this camera acquisition pipeline, since there was a fault in synchronizing it with the steel exit, so that we can rule out all of those faulty images from there. Then if you look into A cut, an A cut or abnormal cut is something like here. You see a small nick over there which looks bright yellow. A bird is something which you are able to see over here. Now mark the thing, the illumination of this image is really bad. So this peeled off version which I see over here, it's not so evidently visible. An N cut or a normal cut is something which would look like this. So that's a perfectly finished out cut. I don't have any defect over there, and I'm generally very happy with that. Now, they are all which are associated with the tail images. Now, with the central images or the full body images over there, I will be able to see grooves. Now, this is an example of a groove mark, and this is a slab which does not have any. Now, you can have these horizontal marks. Now, they are roller pressing marks over there, but they are not grooves. Now, a groove is something like this, which, so because it screeches out through the length of this whole slab over here, so it have a constantly visible mark over there, a very persistent mark, and that's a groove mark which comes out. And this is an example of a double cut. So if you look over here, you would see this thin line which you see over here. So this is the upper torch which was trying to cut, but then it did not have enough of flame power, so it did not actually cut through it. Whereas the lower one actually blew and cut it out. Plus there was a synchronization issue. That's why it still came out, but there was a half mark over there. Now this itself is a defect, because what happens is that the end part is not actually fully finished. So if you're putting it down to the next flow line, then it will not work out perfectly. So for our total working over here, what we did is something like this. So we essentially created a two-level inference for this vision problem. So the first job is to find out like what is the kind of a frame we are looking at. So essentially whether there is a total background, so I don't have any slab in the image, or is it a full-bodied image, or is it a tail image over there? So this is what I need to classify first. Now, if it is a full-bodied image or a tail image, then put it to the next level of working, which is with this patch level detection. So what it does is essentially it tries to look into these two different categories of images. For the full-bodied images, it has one set of algorithms which keeps on working. For the class of tail images, in order to identify the faults in the tail image, it has another set of algorithms which keeps on working over there. So this was trying to break this problem into a set of hierarchically disassociable blocks so that it works much easier for us. Now, if we look into this decision making over here, so what we try to do is that once you have a slab and it goes into this inference service over here, the first job is essentially to break it down into whether this was related to a full-bodied image or a tail image over here. Now, in case it's something which is associated with a tail image, then you come over here to model 2A. So model 2A's job is to find out whether there was a abnormal cut or a D cut or a burr present in that one. And in case none of them were present, then it's a normal cut which goes out. Now, if it's a full-bodied image, then pass it down through the classifier which is in model 2B and find out whether there is a groove or an N groove. So N groove is normal, which comes out over there. So once this is present, now comes the point, like how did this smaller patch level classifiers actually work? So that's interesting. So what we did is, instead of trying to push in the whole image, now this image is really a large size image, and if you want to do a full resolution analysis of this one, it gets really tricky to do it. So what we do is we typically extract a set of smaller size patches. So these patches can, so I cannot tell you the exact specification. That's a IP protected issue over here, but these patches can be something as small as say 200 cross 200, 224, 224, or 224, 224 is something which is very common in case of vision problems deriving themselves from ImageNet. So we actually take 224 cross 224 sized images or something of the same order, and then you train these convolutional neural networks in order to identify whether the kind of defect is present in them. Now, what I do is I have this complete big image. From there, I have random set of sampled out versions of these patches coming into, and then for each of them, we have a decision being taken. Now, once the decision is taken, we also apply a inferencing analysis model on top of it. So what this inference analysis model does is essentially it associates a power of this decision. So if I'm taking a decision that there is a groove present over there, then what is the probability with which I'm telling that there is a groove? If I'm saying that there is a cut mark, there is a burr present, then what is the probability with which I'm telling that there is a burr present over there? Now, as a result of which, not only that we are able to tell a decision, a final classification, whether something is present, we are also able to tell the confidence with which we found it at the location where it is present. So there are three things we are solving. We are telling what is the nature of abnormality, when is the abnormality being seen, and what is the confidence with which I'm making a decision indicating that there is an abnormality present over there. So this together is a very important contribution which comes out from this pipeline. Now, when you look over here, so typically what comes out is that you have these multiple patches which go into this one. And when we are looking into this activation maps through this global average pooling, then what it does is it actually gives me these different activations coming from different places. And for every single class over there, I have a different weight associated. So finally, we fuse all of them together in order to come up with this kind of a class activation map. Now, I have an image just after that where I will actually show you what it looks like. Now, once you do that, then you are able to come to a decision. But what's very interesting over here is that we need to remap each of these patch level decisions back onto the image level decision itself. Because when I have this complete, like the whole steel slab passing through the process and then coming out of the process, and I need to make a decision, the decision has to be made not at those small patches of 224 cross 224, but I have to trace the origin of this patch back to where on the steel slab this was located. Only when I'm able to trace it back to the point on the steel slab where it was located, then I will be able to tell with a sufficient justification that what was the location of the defect, what is the type of the defect, and what is my confidence in saying that that is a defect. Now, mark one thing. I did say that for these tail images where you can have tail defects coming out, there can be burr mark and there can be abnormal cut. There can be burr and there can be a D cut, which can occur together. So now what this would mean is that I will have to export. So this system also needs to give me a confidence map of telling what is my confidence in saying that there is a burr, also indicating where exactly is the burr. Similarly, when I want to show a D-cut, I should be able to show where exactly I found out the D-cut and what is my confidence. If both of them are present together in the image as a defect, then I should be able to tell both of them as well, including the location and the confidence for each of them. So these are certain constants which we need to achieve in order to come up with an explainable model. So that's what we actually end up doing over here by being able to trace back my local context or from these patches onto this full slab sized images. And they are done on a piece by piece basis. So for every single output node over here, so for every class, I have a decision and a confidence coming. When I map back, I map it separately. I don't merge all the classes together in order to map it back. Since it is being done separately, that helps us in a way to identify exact location and confidence of each of these anomalies coming from here. So if you look into this total inference model over here, then from this inference, you would find out that what comes over here is this kind of a confidence map, and that can be color transposed on top of it in order to see it. Now here it shows a burr defect. Essentially, you would see a very red heat map over here, which it indicates this burr. Let me come and actually show you what we were using. So typically for training this one and in order to test it out, we were using a bunch of these images for each of these categories. So it shows how many and these are not patches. These are full bodied images which we are seeing over here. How many of them we had used for training, how many for validation, and in total how many images were present across all of them. Now these are some of these examples. So this is an A cut. This is a background. This shows a burr defect. This shows a double cut, which you see over here. This has a groove mark present over here. This thing over here is an N cut, a perfectly normal cut, and this is a N groove, which is there is no abnormality, so there is no groove present over here. Now, when when we were doing out these patches, so what we did is we actually took out multiple of those patches. Each of them were marked over here. They were brought back onto what image. So these annotation or the file name kind of thing which you see over here is essentially a whole label which says out like what is that abnormality which is present over here. Now we actually had to build up a very detailed annotator tool in order to do this one. Now, please don't think that you just need images and then everything is solved, but you need annotated images. So you need an expert in steel process understanding who actually sat down, annotated with a computer mouse on every single point of where the defect is. And this was again cross-verified by another expert on steel surface inspection. So there were two people who sat down and actually did this whole thing. And finally, we got down these 8,700 sample patches, which were what was used for training our model. Now, once you do that, let's look into how it looks like. So essentially, on this image over here, which is this input image on the left-hand side, you would see that there is an A cut. So this is the defect over there. Now, when we get this heat map produced, so this is the heat map of this abnormal cut, A cut, you can see that it actually fixates itself over here. Now, in order to get that much better visualized, we actually did an alpha blending over here and show this final output. So you get sort of like a thermal map, which shows exactly the region where this fault is detected. There are several of them. I did not give those images. I mean, actually you had this small streak of a line if you have some sort of a D cut and all of those visualizations being shown. When there was a groove mark, then there was a horizontal streak of line which was also coming out over here. But this is what is critical, because this part, what I'm showing over here, is essentially your timing sequence of how these cameras acquisitions need to be synchronized over there. So typically what happened is, like, if you're looking at the direction of movement of the slab, if this is how the slab is moving from my right side to the left side, and I have my camera which is fixed. So initially I would get down my head image over there. Now there is between the head to the first full bodied image where I need to check for my groove, I have typically about 20 to 30 seconds of a time in which I will have to do. So that's based on the speed at which it moves. And again, it's not a constant speed. There is a variability in the speed also which happens. Similarly, from the first one to the second full bodied image, I essentially have just about 2 seconds. So the camera acquisition time itself is variable. So my temporal sampling with the camera, it's not a video camera, it's still a still camera. You can shutter it out at different times. So the second one is taken after about 2 seconds, and right after the second one is taken, in another 2 seconds, you would come down to the tail image. So from one slab to the other slab, you have roughly about 30 seconds of an entry time. But once the slab enters, now you need to fire up every 2 seconds in order to acquire all of these images. So this is where it gets really interesting to look into how this has to be processed. Now, this creates another problem, which is the whole pipeline, which I said, there is a 2-stage pipeline. In the second stage, there are 2 models. So there is a switching of context, which is happening over there. And this complete like nested model is something which on software has to run within this time of 2 seconds itself. Because if it doesn't run in 2 seconds, then the next image would have to wait. And if I'm keeping on waiting, then my defect slab actually goes out. I don't have any more of time in order to move it to left or right based on whether I send it to the exit or I resend it to my reheating furnace over there. So that made us reinvent a lot of these pipelines on the software because they were running on servers which do not run on GPUs. These are plant servers. You are not using cloud because that's for security purposes. These are on-premise servers on which they are run. So a hell lot of multi-threading. These are concepts I'm not going to discuss, at least on this particular forum. So we needed to do hot loading of models. We needed to have multi-threading being done. We needed to have prefetching of models and prefetching of certain compute part itself. And only in that case, we could achieve this kind of a latency. Plus on top of it, the server is not located closer to the camera. So there is about 10 kilometers of a distance between the server and a camera. And all of this is coming via still a fiber optic link, which makes it at least a savior. The speed is far better. And once we are able to do that, so roughly about 4 seconds is the exit time within which we need to switch. So now you can imagine. So all of this DL models, all of these deep learning models will have to run within this time crunch of 4 seconds in order to do it. Otherwise, it's actually working on a plant and the plant will not be working anymore. So that's where I would come to an end with my part of presentation. If you are interested to know more about these kind of vision techniques and using deep learning, then these are some of these places I generally recommend. There are some on medical and biomedical imaging which are present over there. That's a default because I mean I come from the community and there we have many more such anomaly and abnormality detection problems against varying background which we look into. So you can obviously scout through them and get some interesting ideas which work out good as well. And finally, if you are interested to look more into our group, then please visit the GitHub IO page for our group. It has a lot of resources and people details over there as well. Plus, I have 2 courses on NPTEL and they are rerunning again in January of 2021. So if you're interested on deep learning, then you can enroll for the course which starts in January 2021 as well. So finally, this is the group. Unfortunately, Manoj Sharma, who is the guy who pulled a lot of efforts on this work, is not present on this photograph. We hope to have him on one of the photographs sometime later, maybe. And that's where I would conclude my talk. And before that, if you are interested in getting to know more about industrially translatable AI solutions, then please visit us on AI for ICPS, which is our very prestigious and coveted technology innovation hub on AI for cyber physical systems, which we have built up at IIT Kharagpur. And there are lots of opportunities, including career opportunities in core and industrially translatable research, which you would definitely like. So that's where I would end my talk, and I'm open to take up questions and make this more engaging.
Okay, so thank you, Dr. Debdoot, for a very, very nice presentation of all the tasks carried out by you for solving a particular problem. So we can now see the real extent of industrial level of difficulties or challenges which need to be taken care of to come up with a good solution, and it's very good. So I will request all of you to join me in applauding Dr. Debdoot. Please join. It was a very good
Thank
talk.
you.
And then now it is a session open for question answers. So participants, please go ahead. We can take some questions from your anyone willing can either raise hand, then we go one by one, or I think that's the best way. Anyone having raised hands? No. Abhijit Sadhu. Yeah. Abhijit. Okay. Okay. So you can write in chat. Okay. How do I see? Okay. Yeah, you can write in chat. I can take it. Yeah. Okay, so probably people can keep writing. Until they write, I would like to ask some of the discussion items with Dr. Debdoot. So it's really good. So I think you have worked on real high temperature objects. Is it real high temperature objects? And how could you take care of the temperature anomalies?
Okay, so so essentially, I will tell you what happens over here is that the camera which we use over there, it has a very wide spectrum sensing. So this camera is not a consumer grade camera. This does not have a UV and IR filter fixed in front of the sensor. As a result of which, it can actually sense all the IR range as well, which is more of temperature associated. The bigger challenge which comes out is that because IR itself is very focal and non-uniform, and you have a wide spectrum of temperature difference which comes in. So what they do is we put down a polarizer in front of it. Now you put down the polarizer, it's going to cut down on the IR intensity, but along with that, it also darkens out all of these peripheries. Now, in order to make that uniform, what we do is we now have these extra halogen lamps, real high power halogen lamps, which are put over there so that, so in one of these examples, let me show you this slide. So here you will be able to appreciate it. So if I'm seeing these N groove and the N cut, which is on the right hand side, maybe a bigger image would be better. So if you look into this N groove or this groove mark images, you would see that this is something which comes from a slab which has pretty much cooled down. So you don't have this thing due to the IR. This is a pure illumination which is coming down because of the reflection from the halogen lamps over there. The only thing is this camera's exposure time and the ISO levels, they need to be changed every time. So in fact, within that 2-second thing which I was saying, within that 2 second, we actually push a lot of command sequences to this camera under varying exposure levels and ISO levels. A burst of images are captured. Now this burst of image is again passed through another processing pipeline, which just looks into quality of image factor, and then it exports out only one image. There is something more which we are trying to do with HDR imaging, HDR from the IR to the visible range, but again, that's something I cannot disclose at this point. That's another solution which helps us get better quality of images.
Yeah, thank you. So in the meantime, I got two queries. One from Dr. Dev Gupta of Arizona, US. He would like to know what were the hit rates, correct recognition of defects of your system, and do you simultaneously do simultaneous imaging with IR camera like FLIR systems?
So there is no specific IR camera. We just have a wide spectrum electronic sensor. It senses from IR to the visible range, everything over there. There is no specific separate IR camera as such. It's just one single camera, one camera which is placed on top, another camera which is placed at the bottom of the steel slab. But I'm not showing this bottom of the steel slab inspection. These are all taken from the top of the steel slab.
And what is the hit rate? What were the hit rates?
Yes, so for each of them it was different. I cannot recall, but typically we had a lower hit rate for A cut, which was about 95% of the times. But for all others, it was above 98% of the times.
Yeah, I think that was answered, Dr. Dev Gupta. If you have some more, you can keep writing. I'll take it up. There's, I think, another question from Taksh. In the data set, D cut has relatively less data. So how did that bias get balanced? So how did you less number of samples for D cut? Yeah.
So generally people associate less number of samples with creating some sort of a bias, but that is not the case. If you look into machine learning literature and try to understand it from a representation space perspective, and then draw in all sufficiency criteria from Bayesian decision making, what we want to have is not a lot of samples which look similar to each other. I would like to have sufficiently distinct samples. That is when I will have an unbiased data. A lot of samples which look same and very similar to each other is still going to create an unnecessary bias over there. So although in D-cut you did see the number of images less, but the spectrum of their appearance was pretty wide enough to capture it, and it did not make the system biased.
Okay, yeah, thank you. So another question from Mr. Raju Prasad. That is nice presentation. He appreciates. Then how are you predicting undercut defects at the head and tail? In addition, what about internal defects?
So we don't deal with internal defects as if you want to, yeah. So side of slab defects is something which we are not considering as of now. And there is a reason why we don't consider, because the cast in which it comes out, the sides are actually going through a continuous roller. So the side does not have actually any defect over there. It's a continuous roller from which the only point where it comes down is when you are dissecting the slab and then it's getting rolled out and all of this. That's why, at least for this particular steel plant, we don't have side defects. So
No, rounding of the edges and the edges.
I did not quite catch that question. So,
Mm.
so the point is, on the side, there will be two different types. So what I got to know, at least by discussing with them, one is like, if you don't have a ruler on on this side over there, so when you are pressing it down, then there will be a non-uniform expansion on the sides. So they tackle that by putting down a whole series of rollers. So you don't have non-uniform expansion when you are compressing it on the thickness side of it.
Maybe he's telling the bulging out things at the edges. So
Okay. So the bulge is also stopped in a way because these rollers are pretty much orthogonal and end-to-end rollers.
yeah.
So this is sort of like a production side thing which they ensure.
Yeah, I think it's answered. If you have some more queries, you please write.
And I think there was one question which was like internal defects. So internal defects also we are not able to do it because you would need X-ray imaging in order to be able to do it. We are just looking at surface defects.
One more question has come from someone operating this is how machine vision will play a prominent role in augmented or virtual reality cases for steel industries, AR, VR cases in steel industries. How machine vision can play a prominent role.
And I mean, most of the things, whatever we do with augmented reality actually has vision as the bigger component, since it has to sense the physical environment before you start augmenting.
Yeah.
Now, it's more of like a philosophical question how it will play a role, but I think it's already doing, at least in the steel plant in Jamshedpur. I had already seen maintenance workers working with augmented reality goggles over there. So some of the service technicians who work out on the bigger chimneys and high-rise places, they actually have those augmented reality goggles and a complete monitoring of what they are doing through a vision assistant. So it's there. Bigger impacts would be in maintenance operations where you need humans to come in. But at least these are places where we are trying to do all of the quality control and everything in a human-less, as less humans as possible in a way. If you don't have a human, then why would you put down all the augmented reality to work out?
Yes. Yeah. I also, I think I did not get any further questions, but they might come up anytime. Well, I have one more query is you were time synchronizing. So how could you do this? What's your processing rate or lapse rate? How did you adjust that with real-time systems, or did that influence back on the Tisco or Tata processing plants timing, or how was it done?
It's pretty much dependent on the processing plant timing. But then what happens is that first we have this. So at the start of it, how it works out, at the start of it, you have this camera running in video mode, and it's at a lower ISO level. And what we are just trying to do is that we are trying to find out whether this steel slab has entered. And there is a very simple trick to that. You have this camera which is doing 25 frames per second. Just below the camera, over there, there is a light. There is a specific green colored light which is placed. Now, the green colored light is something which will not come down when the slab enters. So when the slab enters, that light gets cut off. So you know that the slab has actually entered. So that is my trigger. That is my first start of the slab entry. So that corresponds to this head image. The reason why I said that I don't have a head image, because there is a lot of green halo over there. So this is just used in order to time it out, saying that, okay, I'm starting this slab acquisition. Once I have this head which enters over there, right after 2 seconds, I take a full body image. Then after another 2 seconds, I take the next full body image, which is at T3. So T2, T3, you have a 2 second timing interval. And right after that, another 2 seconds, and you would be getting down an end image over there. Now, once you verify that there was an end image which comes out over there, you again turn on the green light and keep on waiting in the video mode.
Yeah, very good. Any other question from the participants? It was really very, very exciting and enlightening. I can see that. Any participants have any other questions? Please put your questions on the chat box. And I also would request Ms. Pravanjan, are you there? Yeah, can
Yes.
you? Yeah, can you? I think
Yes, sir. I'm
we
sharing.
will wait for 2-3 minutes for questions, and then we maybe conclude with your small presentation you have in mind. Which can go ahead, and then how do you go ahead? How do you plan to go ahead? We wait for 2-3 minutes for any questions from any participant. Okay, so Pravanjan, can you present your screen and then go for announcing? Yeah, we should thank Dr. Debdoot, working with IIT Kharagpur in the Department of Electrical Engineering, for his very, very enlightening talk today. And it's actually in tune with all vision-based and machine learning-based approaches, and how actually to solve a small problem, a lot of things have been taken care of. So we know it's really challenging, but it's doable. So that's how we come up with a good solution which is existing. And of course, it should not be in cloud, but it should be with a lot of other computing facilities within the in-house capabilities of the industry, and of course a lot of parallel multi-threading tasks performed to get it done in perfect time. So I wish again to congratulate Dr. Debdoot on his presentation today, and it was really very, very enlightening. So there is one announcement from the Center of Excellence for Advanced Manufacturing Technology, which is getting displayed. A 6 days training course on industrial robots for students and industry professionals is scheduled from January 17, 2022 to January 22, 2022. Last date of application is January 15th, and the email is also given. Yeah, so if there is no more queries, upcoming webinar in December, I think next week, December 25th, we have a presentation by Professor Renshu Gu of University of Hadarshil on topic on rotor sensing of spindle vibration for online motoring machine processes. So yeah, with this, okay, so another slide for next 2 more presentations to come in January, on January 1st, 2021 or 2022. It should be 2022, and January 8, 2022. Yeah. So by
Yes, sir. It is a typo error.
George F. Vanderbilt, consultant in metallurgy, failure analysis, and archaeometallurgy. Topic is metallurgy of welding process. And then the next week, January 8, 2022, by Mr. Sanjeev Kumar, CGM IC Services, ISCO Steel Plant Burnpur, topic Industry 4.0 in steel making. Yeah, so with this, we can, yeah, you can have the past webinars on scanning this QR code. And yeah, so with this, I pass it on to Prabhanjan, and we can have a vote of thanks from Prabhanjan.
Yes, sir.
Yeah.
Yes, sir.
Can you offer vote of thanks?
Yes, sir.
Okay, so on behalf of the organizing committee of this series of web series of Institute webinar talks on Saturday Talk for Manufacturing, I take the privilege to offer vote of thanks to Dr. Debdoot, Professor at Electrical Engineering, IIT Kharagpur, for his very nice presentation on the use of vision for processing or manufacturing defects, identifying manufacturing defects, a very challenging problem with dynamic background. Professor Debdoot has really given a very good insight into the problem and the different research components of the same small industrial level issues which can be solved. And there are lots of other questions. Some of them have come up in our chat box. And of course, if someone else wants to, come up with some more discussions, either he gets in touch with Professor Debdoot or Professor Surya Pal, who can get in touch with Professor Debdoot. So let us all give Dr. Debdoot a very big hand. Thank you. And we conclude today's session.